Okay, let's continue our discussion on probability. So in the homework, I think one of the in this homework, one of the example is like this. Do we have this? No? Okay. Anyway. Now let's talk about other examples. We have defined the conditional expectation, right? And conditional expectation can be used to compute expectation. Or it's just like this. I think in the homework, I think in problem 2 is all about this, right? How to use conditional expectation to help you compute expectation. Because sometimes the conditional expectation is simple, okay? So this is also related to the law of total probability, which you can think about them as divide and conquer. You divide the complicated case into special simple cases, and you sum them together will give you the total result of the overall expectation, right? So I'm not sure how can you understand this formula? If I want you to compute, prove this, how do you prove? How do you compute? How do you prove this formula? Or does this formula even make sense to you? How about you? 直接展开，展哪边展开？ But okay, all right. When I ask you to prove, how do you prove? You have to go to definition, right? You go to definition. You say, okay, this guy can be written as this. You should write down. I don't want to prove this, but let's try. Okay. It will be very simple. This is by definition, integral is summation, right? Sum of all the possible values capital X may take times the likelihood this value occurs, sum them together, right? I'm repeating this argument, okay? But you want to use conditional Y to compute this marginal. So that will be, if you like, that will be what? Marginal is nothing but the joint dy. This will be my marginal, right? You integrate out all the y possible values. Then you times dx. Okay? But I can move this integration out. Typically, I don't write two of those integral symbols. Okay, to me, it's the same. Okay, it's clear from the context. This will be x times the joint. Joint is nothing but x conditional y, small x y, right? Then what is it? Times marginal of y. This will be joint. Okay, and then you have dy dx. Okay, so if you group them smartly, that will be integral of x. Let's do it carefully, okay? Yeah. So then inside this, I have integral of x y given y, x given y, dx times margin of y and dy. Okay, this inside this, I'll call this part, is expectation of x given y equal to small y, right? And times the likelihood this small y occurs, and sum them together again, you get the expectation of x. Well, we don't have to prove this, but since I just show you, okay? by definition, everything should be simple. The only thing that you somehow feel hard maybe is just it's mostly about the conceptual understanding, okay? I don't want you to remember too much. It's just understand all of them. You can write down those formulas immediately. Similarly, I will say this guy in the homework 2 as well, the problem 2 homework as well, it's if I want to say any function of x, y, they can be written as expectation on y. So this is again a divide and conquer. So for example, this guy could be any function of x and y. For example, I can say g of xy is x squared plus e to the y. Some weird function, that's fine. If I want to compute this expectation, all I need to do is sum all the possible values this guy takes and times the likelihood its value occurs. Okay, so we'll give an example to see how this can be done. But here, my emphasis is that doing expectation can often be simplified, sometimes I would say, simplified by conditional on some other variable, and you divide into different cases. In the sum or over all the possible cases, will give you that formula. So this you can also derive on your own. Let's directly look at the example. The same example as example 1, but now let's talk about, I want to compute expectation of x. Okay, so I can use two different approaches. Method 1, expectation of x. First of all, I need to find the distribution of x, right? So how many values it takes? What's the probability each value occurs? Then you sum them. That's it, right? So first of all, let's compute the marginals of x. So x can take, how many values x can take? 2, 3, 4, 5, 6. Okay? What's the probability of each of this value? What's the probability of x equal to 2? How do you compute them? You should sum over all the possible values of y, because you don't care about y. You only care x equal to 2. So in this case, x equal to 2, all the others are 0, right? So that's also 1 over 4. X equal to 3 is the sum over this column, which will be 7 over 24. And then you sum over all the three numbers for equal to 4, 7 over 24. That's weird numbers. Equal to 5 is 3 over 24, or 1 over 8, right? This is, guys, 1 over 24, okay? They sum together, all the 6 numbers summed together should be 1. That's the marginal. Then I can compute expectation of x equal to 2 times 1/4. The value it takes times the probability that value occurs. And you sum over all the possible value it takes. 7 over 24, 4. I don't want to write all of them. Eventually got a number, okay? Do you know what this number is? I don't care. So some number. I don't care about numericals, okay? Because the computer can do this much better than human. But you have to understand what you're doing. That's first method. I can also do second approach is method 2. I can do this. Expectation of x is, I can condition, all right? Expectation of x given y equal to, let's say, 1 times the probability of y equal to 1. Divide and conquer. I divide according to y values, okay? Plus expectation of x given y equal to 2 times the probability of y equal to 2 plus expectation of x given to y equal to 3 times probability of y equal to 3. It may be more tedious. It's not simple, but it's the same. I mean, mathematically, sometimes this is simple. Sometimes this is easier to compute than directly computing the marginals. In this case, it's maybe not simple. And from the previous slides, I think we computed this number, right? This was 1/4. Okay? That's the conditional expectation of x given y equal to 1 times the probability of y equal to 1. What is it? You need to sum over the entire first row, right? That will be 1/2. Okay, that's the first term. Then you need to do second term, third term. We didn't compute because I asked you to compute. So here I'll ask you to compute as well, all right? Please finish by yourself, okay? It does not add value to your understanding. It's just numerical computations. Okay, overall, we'll have a number. I will say some number 2, some number 1, and I will say you need to check these two are the same. Okay. I don't want to compute it to convince you. I could tell you this is the same. I think you can imagine it will be the same. And we also prove it mathematically like this, right? Mathematically, it's just this conditional expectation, divide and conquer. Okay. Now let's look at numerical example. Another example 3. That will help you to further understand this thing. And let's say example 3. Outcomes with equal chance. Suppose I have x and y, okay, distributed according to this. So it takes this pair of value, right? X equal to 1, y equal to 1. How many value it takes? 1, 2, 3, 4, 5, 6. With equal chance means it's 1/6. Okay, now I want you to compute. I want to define g is a function of x and y. I want to compute, please compute, expectation of x squared, y squared. I think this is this table is like this. So x and y take 3 values, right? Each of them, and it's basically 1, 2, 3, 4, 5, 6. These 6 values occurs with equal probability. So each of them is 1/6. That's the statement of this problem. And the first method, I want you to check. I already typed in the solutions. And expectation of this is nothing but expectation of x squared, y squared. How do you compute this? This first method is expectation of x squared, y squared. It's all the possible value this takes. The only randomness comes from x and y jointly take some values. Each of this occurrence of this value will give you a value of x squared and y squared, right? So that will be, it's only possible 6 cases, right? So it's 1 squared times 1/6. This guy is 2 squared times 0 squared times 1/6, right? It's x squared, y squared. And the third one is 2 squared times 1 squared times 1/6, equal to 1 eventually. It's not the probability, but it turns out the expectation equal to 1 if you write it down. The only thing non-zero terms already list them here. That's first method. Let's look at the second approach, right? Method 2. The reason I want you to go two possible ways to compute this is really throughout this process, you can gain understandings of conditional expectation. And all we need to truly understand Kalman filter is have a solid understanding of conditional expectation. Okay, now let's condition on, so let's condition on y. Okay, let's see what possibilities of y it could, what all the possible value of y could take. Y could be 0, right? It's true. Y can be 0. It's this row, right? And in this case, if y is 0, x squared y squared equal to 0. Okay. What about y equal to, what else y equal to? Y could be -1. Okay. Y equal to -1, then x can only be 1/6. There's no also other cases of x. So in this case, x squared y squared equal to, it's just 1, right? Does it take multiple values? If y is -1, then x is fixed. So x squared and y squared multiplied together is also fixed. That's one value. Okay. Well, another case. What about y equal to 1? So then I will say x squared and y squared. What are the cases? The first one is the value it takes is 1. Because that will be x, because when y is 1, x can take these two values. Okay? So only these two values, so they will be, if it's 1 with probability of what? So what's the probability of, in this case, is x equal to 1 given y equal to 1. Sorry, is that true? Yeah, yes. Okay. The other case is x can also be 2. X can also be 2. Then that will be 4. This value will be 4 with probability of x equal to 2 given y equal to 1. So now let's I divide into these cases. Now let's look at how we use it. The first one, I will say expectation of this, first of all, given y equal to 0. What is this, Xiaohan? You have to be able to tell. It's 0? Why? This, okay, for you, maybe half an hour ago or yesterday, you will feel really confused about this ugly looking formula. But now I want you to think clearly. When y equal to 0, y is fixed. X squared, y squared is something you want to compute for expectation, right? This x squared times y squared can still be random. In this case, it's extreme. It's just take one value now, right? So it's just what? No matter what x is, y equal to 2, or y equal to 0 tells you this thing can only take value 0 with whole probability 1. If you like, it's just that. So it's 0. Very simple to compute. Okay? That's condition, right? So what about y equal to -1? It takes only one possible value again, right? As I mentioned before, it's 1. So it's 1 times the probability 1 is 1. Are you with me? Okay. Now I will say the third case, only possible 3 cases, right? Third case is y equal to 1. Then what's the conditional expectation? y equal to 1, now x squared, y squared can take two possible values. The first one is 1, which happens with probability this. What is it? Do you know what is this? It's x and equal to 1, y equal to 1 divided by y equal to 1, right? This is, I think it's, you just look at this case, they are equal, right? It's half. The other one is also half. This guy is also half. They sum together equal to 1. So when y equal to 1, x squared, y squared take two possible values. Each of them occurs with equal likelihood, which is 1/2. So this is a half plus 1, the other one is 4, right? 4 times 1/2, which gives me 1/5, 5 halves. Okay, divide and conquer, I divide into 3 cases. Okay, now I can sum them together. So overall, if I don't care about what y it is, I need to do the summation. It's like divide and conquer of the law of total probability. So what you have is, so expectation of x squared, y squared, given y equal to 0, times probability y equal to 0, plus expectation of x squared, y squared, given y equal to 1. Let's use the second case, is -1, right? And the times probability of y equal to -1, plus expectation x squared, y squared, given y equal to 1, times the probability y equal to 1. What we have here is, this guy is 0, right? Doesn't matter. This guy is plus 1 times probability of y equal to 1 or -1. What is it? No. Oh, yeah. -1 is summation over this row, which is -1. Which is 1/6 plus this guy, which we have 5 halves times -1, which is 1/3, right? So overall, I have 6, 5, 6. Oh, it's 1. It's the same as this guy. Why we need to do 2 approach? This helps you understand how you do divide and conquer. Can I condition? Okay, so if I do this, can I condition on x? Yes. I can also condition on x times y. Whatever easy for you, you can condition on something. So you divide all the cases into simple cases. It's easy for you to understand. Then you sum them together. Okay, if you haven't fallen asleep, that means you're good. This is very tedious and simple, but I want to make sure you understand the steps so that you can do hard stuff, okay? When we study joint distribution of 2 variables, the most critical thing, of course, joint density and conditional density. The another good metric or definition or concept is covariance matrix. 这叫什么？斜方差矩阵。Okay, covariance matrix. I think you all have learned covariance, right? Do you know what covariance really is? To save time, I don't think you have those written down, but I have those data. Okay, covariance by definition. Whenever I draw this triangle, means definition. Definition means I don't need to explain, right? It's how I define it, how people accept this definition, they will use it, okay? It could be useless, could be useful. And in this case, the covariance definition is very useful. What this is doing, expectation of x minus the expectation of x times y minus expectation of y. It looks, this guy is a number, okay? It's a deterministic number, right? This guy is another deterministic number. You can think about them as 2 or 3, whatever. So it's basically the randomness comes from where? This guy and this guy. What it's trying to do is expectation is sum, is summation, right? So this multiplication is random. It takes multiple values. You always start from this, okay? It takes multiple values, and each of the value occur with certain probability. You sum them together. Okay, let's look at sampling data example, sample data. I like Shenzhen temperature so much because now it's Shenzhen temperature from January to June. Wonderful temperature, right? But I don't feel it's wonderful, it's hot, right? The average temperature is like this, 20, 21, 21, 27, 30, 31, okay? Guangzhou seems to have better ones. 19, 20, 22, 26, 20, 30, 32, okay? I have 6 variables, 6 sample points. And the mean, the average for Shenzhen is 25, and for Guangzhou is 24.833, okay? So xi minus mean is how much you deviate from your average value, okay? Can you see? And what this covariance is doing is that this minus mean and y minus mean, they multiply together. So this guy multiply this guy, okay? And this guy multiply, right? You sum them together, what you will see is that, okay, whenever Shenzhen, this is real temperature, I downloaded, sorry, I found from website. It's not that my makeup numbers, okay? So they're real. So whenever this guy is below average, Guangzhou seems to be below average as well. And the average is the first half year average, okay? You can see that the signs are the same, are exactly the same in this case. Sometimes maybe off a little bit, but in this case it's exactly the same. So whenever Shenzhen is above the mean, Guangzhou is also above the mean, okay? Now I find another city, Sydney, which I think you know where it is, right? So that's the mean, that's the temperature. It's also pretty good. It seems like it's better location to stay, right? It's cooler. And whenever Shenzhen is below its average, Sydney is above the average. Okay, if you multiply these two and sum them together, you will have a negative number. The sign matters, okay? If you multiply xi minus x bar and yi minus y bar together in the sum of over all the possible value cases, and this number will be positive because this negative you cancel with this negative. So overall, you will see whenever this, so this is roughly how you compute covariance, okay? Whenever this covariance is bigger than 0, we call this x and y are positively correlated. If it's negative correlated. Any questions? The number are wrong? The number may be wrong, but I think those columns are correct, okay? If they're 0, then x and y are uncorrelated. What does this really mean? So all it means, you can use y to infer x, or use x to infer y. The reason is that, at least, if you see a realization of x, if you see, let's say today, Guangzhou's temperature is 35. on average, it should be 30. Today is 5 degrees more than average. Then you can infer, oh, because I know I'm positively correlated with Guangzhou, Shenzhen, right? Then I will also be more likely to have a hotter day today. So positive. If you see something above average, if I'm positive correlated, then I will be also above my average, more likely. The other way around, you see Sydney is above the average, and I will say because I'm negative correlated with Sydney, then I will be what? Below my average. Okay, if their correlation is 0, that means I cannot draw any conclusion. I could be more above average or less than average, but I don't know. Okay, it doesn't change my belief. All right, by definition, this is definition. You can also compute by this definition. This guy, this is the example. This is another example. It's not based on sample data. It's based on distribution. So X and Y are jointly correlated. Jointly distributed according to this table. How do you compute covariance of X and Y? By definition, X minus EX times Y minus EY. Okay, so I first need to compute EX, right? EX, in this case, 1 times 0.25 plus 2 times 0.1, which is 1.75. Yes. Yeah, sorry. That's wrong. Because you need to sum over all this, right? The expectation of Y is, this is a -1 times 0.35. You need to sum over this row, plus 1 times 0.65, 0.3. So the covariance will be what? Just copy this, right? How do you do this? Summation. When you see expectation, it's summation. It's integral, it's summation. What value it may take, the only possibilities of all the combinations of this pair valued, you need to sum them out over all the possible cases. So the first one is, so this guy is 1 when X is 1, right? 1 minus the expectation, 175, times Y is, let's say, -1, minus 0.3 times 0.25. The value it takes and the probability that value occurs, that's the first case, plus the second case is X equal to 2 minus 175 times Y equal to -1, right? -1.96 times 0.1. Okay, I don't want to write all of them, only 4 terms. Okay, eventually you will have a number which is some number, right? I don't care. You know how to compute, the number only counts you maybe 0.5 points in the final exams. But if you compute this wrong, then conceptual mistakes, I think it's worth more penalties than numerical calculation mistakes. Now you know how to compute this, all right? You know what it's meaning. But that's only for scalar cases. I compare pairwise. Now I'm going to introduce you the covariance matrix. I'm going to draw a triangle here. What does this mean, Xiaohan? Definition. Definition means it's defined this way, right? Okay. So now X can be, so X is Rn, Y is Rm. It's vector. So by this definition, I know this guy is what? Is the expectation of x, let's call it x1, x2, all the way to xm, minus expectation of these things, which is also a vector, right? But this is a deterministic vector. Do you understand why it is deterministic vector? You only take one value. It's just if you do integration of some random variable, you get a value. Okay, so that's this guy times y, right? y1, y2, all the way to ym, multiplied by expectation of y1, all the way to expectation of ym. And you take a transpose of this, okay? So overall, you will have a what? This is n by 1 vector times m by 1, and it will become 1 by m. You can take a transpose. So overall, you will have, does this multiply? Overall, you will have a n by m matrix, right? Is n by m? Yes. So each element of the matrix have the following meaning. So the first one is the covariance, the scalar covariance between x1 and y1. The second one is x1 with y2. If I ask you, Suyan, I want you to prove this covariance, I can write like this. I want to prove this. How do you prove? By definition. Yes, exactly, right? By definition. Because you should know how to, you should not say, well, I didn't learn this. You learned because I tell you this is the definition of this, and the expectation is nothing but summation or integral. Do you know summation about matrix? Yes. Then you know this expectation. You can just find the formula in, I mean, if you compute all the elements, it will be just that. I think you can imagine what will happen if I multiply this out. You can see this will become the first element will be x1, ex1, right? Multiplied by the other thing. You know roughly how it will turn out. I don't want to write down all the cases, okay? Any questions? All right, so let's work on an example. Oh, I have so many properties, by the way. Do you need to remember? I don't think so, because all the things will be open node. But you need to understand them, otherwise I don't think you can use them, right? I will say here, my favorite word, right? Verify yourself the 6 properties. But today, I think how much time I have? 5 minutes. 6 minutes. Okay, let's try prove something. Let's say which one you want me to prove. The 5th one. Okay, let's say this guy. All right. What else? So yeah, you pick one. Let me do this, okay? Let's first do Yuntian's request. If x independent of y, covariance of x, y is 0. This is more general case. I'm talking about what? Vector case, okay? So in this case, let's assume expectation of x, let's call it a. Okay, it's a number, right? Expectation of y is b. So then I will say expectation of x minus, ex will be a, right? Let me just change that to a times y minus b. Let's assume this is a scalar case, okay? I don't want to complicate the notation, but is that okay, Yuntian? Scalar case will show you the essential part of the idea. What's the condition now? Is x and 1 are independent. Okay, so that's, if you write down the definition, first of all, this definition, what you have is two integral, right? X minus a, that's small x now, right? Times y minus b times joint distribution, dx dy, that's my expectation, right? I say they are independent. What I can write further is that this guy can be factored. Okay, so that's, it will be equal to, I can write this guy as fx multiplied by marginals. Okay, then this will be x minus a times the marginal of x dx. And factor, then times another integral of y minus b, marginal of y times dy. Okay, these two multiply together, you will see this is always 0. Why? Because this is nothing but x, fx, x dx minus a. By definition, a is that. The reason I can move a out is a is deterministic. You integrate over 1, any number a times fx dx is always a, right? Expectation of a constant is a constant. The reason is it can multiply out and the integral of density is 1. Okay? So that's 0. So I know this is 0. I hope that's enough. And this guy is something you have to be familiar with later on. It's also from definition. Okay? Because this is expectation of ax minus e of ax times by minus e of by transpose. All right? So you know this is deterministic, a can be moved out. So overall you will have expectation of a times x minus e of x times y minus e of y transpose times b transpose, because I factor out b, when I take transpose, b somehow move to the right. Okay? Overall you can pull this out, so you get that formula. So the multiplication of a deterministic matrix will go to the left and the right. If you go to the right, the second argument then become b transpose multiplied from the right. Each of this, somehow you should try to prove it. It will be very simple. If you find it hard to prove, that means there's some kind of gap in your, or holes in your understanding. Okay, hopefully, we haven't finished. Yes.第六项这个 covariance of x is defined as the covariance of x with itself. It's also called okay. Covariance of x in the vector case is covariance with itself. This is the square matrix. This is square matrix. Okay, you will see a lot of covariance matrix later on. If a single variable, that will become a variance. Okay, in matrix case, we'll just call it covariance matrix. All right. Last time we were here, we start introducing the covariance of two random variable, and we extend it to covariance of two random vectors. Okay, and the definition, I gave a quick recall of the meaning of the covariance, as well as how to compute them for random variables. Then we jumped a little bit to define the covariance between two random vectors. They may not be of same dimension. Okay, it could be Rn and Rm, and then these two covariants become a matrix, and each element of this matrix is the element-wise covariance between xi and the yj. Okay, so Shuyan, how do you prove this? I want you to prove the second row and second column is just this. How do you prove? Whenever I ask you how to prove, is by definition. You just start from definition. The definition I wrote down here, right? This is the definition, and you look at this definition, and don't be scared of this expectation symbol. It's nothing but summation or integral. Do you know how to do summation of two vector? A column vector times a row vector, basically, right? So you know it to be a matrix, a summation of bunch of matrices. And you find out the second row and the second column of that matrix will be exactly of this form. So you can prove everything I tell you, but I won't go over all these details, right? Okay. Shuyan, how do you prove this? By definition, yes, 100% correct, right? So what I mean by this is, I don't want to prove this, okay? These are deterministic constants, okay? What's the meaning of deterministic again? Single value, not multiple value, right? There's no distribution. And how do you prove this by definition? Let me write down here. The definition of covariance is nothing but transpose this, right? If I ask you to prove this, then you find out adding a constant or deterministic constant doesn't change this, because x plus a minus expectation of x minus expectation of small a is a as well, because it's constant, right? These two constants got canceled out. So you don't need to worry, right? It's very simple. Each of those properties, although I don't go over them in details, but they're relatively simple to prove. All the proof is by what, Shuyan? Yes, exactly. You just copy the definition in. All right. I think last time is that you asking the sixth property. What's your name again? Tang Yu 什么? Yuxuan. Okay. Yuxuan. Okay. So Yuxuan's question was, this would be called variance instead of covariance. Okay. So but in the vector world, I can call the covariance of with itself is also a covariance of X. So this is defined. I can call this variance, no problem. Okay. But what's the variance of a vector? I can define it as this way, okay? Define that the covariance of X with itself is called variance, okay? And, but I will just say covariance of X. Okay, those are somehow shorthand. With itself. Okay, so why this is a positive semi-definite matrix? Do you remember what it's, did I review that? I forgot. Yeah, so this, yeah, we didn't review this in detail for the first review lecture, but I assume you know what positive semi-definite is and how to show this is positive semi-definite by definition. This time, the definition, you have to know the positive semi-definite matrix definition as well. Because, look at this, okay? If this becomes covariance of X with itself, it's nothing but X minus EX times X minus EX again, transpose. It's almost like X squared, but it's not, right? This is a vector, this is a column vector, times a row vector. And these two vectors are the same. They will give you a matrix, right? And each of these matrix is positive semi-definite. You can easily show that. Rank 1 matrix. It's very simple matrix. It's very useful matrix, actually, this kind of matrix. And the expectation is nothing but with the sum of these positive semi-definite matrices, right? And then by definition, you can still show the result will be also positive semi-definite. Okay, although I didn't go over them, but I hope I gave enough hints or point you to the right directions. If you're curious about this properties, just check the definition. Don't think of, a lot of people ask me, Professor, do you have a textbook or other book that I can use? Because whenever you see something you didn't know or you don't know how to solve right away, you typically think about, oh, where should I have a formula or a theorem that I can directly link to the problem at hand? Or that's typically the habit. But now we want you to think, right? All the concepts are defined, I think, clearly by my lecture note already. You don't have to have another textbook. All right, so let's work on a few examples. The first one is almost like a pure exercise for the definition. Just get you familiar with the covariance between vectors, okay? Suppose, let's say X belong to Rn. Those are all symbolic, okay? Y belong to Rm. Now I'm going to ask you, what's the covariance of, what's the dimension of this matrix, covariance X, Y? N Rn by M, right? This is a matrix. Is this matrix deterministic or random? It's the covariance. It's a number, or it can take multiple values still. After you take the expectation, all the multiple value got integrated out, right? There's just one symbol, one number. So this is a deterministic matrix. Covariance X is another matrix. This is square, n by n, right? This is m by m, okay? Now I ask you to, given those things, suppose I gave you, okay? There are numbers. I don't want to write down the numbers. You picture those are numbers of those different sizes of matrices. If I ask you what is the covariance of AX plus BY, and A and B are deterministic constant matrix, deterministic constant matrices, okay? So the covariance would be, so the cov AX plus BY. By definition, I said this is a shorthand notation for, I didn't ask you to prove yet, okay? So this shorthand notation of the variance is the covariance of this vector with itself, okay? And I can write down the definition to compute this, but I can also use the property to compute this very easily. So the property is, let's look at our property. Let's first look at this property, the third one. X plus Y with Y is X with Y plus X2 with Y, okay? So that's, so I can write it like this. Covariance of AX with AX plus covariance of AX with BY plus covariance of BY with AX plus BY with BY. Can you get this? Looks similar to multiply. It looks similar to multiply this A plus B, right? Why is that? It looks like a multiplication of these two. Of this form, right? It is indeed, it is just the multiplication. Look at this. It's the multiplication of these two things, right? So you have this multiplication-like type of property, and once you get here, this is by property which one? Let's say this is by property of 3. The next one is, let's use property of 4. Let's say use property of 4. What you got is, this guy can be moved out. This is A covariance of X with X, A transpose, okay, plus A covariance of X with Y, B transpose, right? And plus, B covariance of Y with X, A transpose, plus B covariance Y with Y, B transpose. Is that right? Okay, so then we can summarize. Based on the condition I gave you, this will be, let's use it. So A covariance X with X, I will call the sigma X. That's a matrix that we define in the statement of the problem. This is A transpose. And this guy is A cov XY, that's sigma XY, B transpose. This is a matrix I gave you. Okay, think about them as a few numbers I gave you, but I don't want to specify those numbers because they are not conceptually useful at all. So this guy is B times covariance YX. What is covariance YX? I only gave you covariance XY. So this is transpose, right? So sigma XY transpose times A transpose plus B times sigma Y B transpose. That will be your answer. A bunch of linear algebra again, right? Any questions? Okay, now let's move on to the next more numerical example. Now I gave you, all right, this is almost like a sigma Z, okay? I gave you the matrix. The numbers look like this. So I know Z random vector, Z is random vector, is in R3, okay, it's a random vector. And what I told you in the example is the following. It's the expectation of Z is 1, 2, 3, and the covariance or the variance of Z is a 3 by 3 matrix that I gave you those numbers, okay? Now I redefine, okay, I regroup the things that I like them. So for example, I say P is the first two coordinates and also swap them. I can do arbitrary thing I want, okay? P is a two-dimensional vector. The first coordinate is Z2, second coordinate is Z1. Is P random or not? Because Z is random. P is defined in terms of Z. So it's also multi-valued, okay? And Q is Z3. Now I ask you to compute what's the covariance of P with Q. Let's, I'm not sure whether you can, but I can see it right away, but I want to go through baby steps so you know how I get there. Okay, there's no formula, you have to think. The only formula I gave you is definition and a few properties. By definition, this is P is Z2, Z1. Q is Z3. Okay, I'm just changing back the variables. Then, what's the dimension of this matrix? 2 by 1 matrix or a 2 by 1 vector, either way is fine. So what I have is, but each of these elements is what? The first row, first element is covariance of Z2 with Z3. Okay? The second one is Z1 with Z3. What are those two numbers? Do you know? Z2, Z3. Can you read this one? So what's the meaning of this, for example? Xiaohan, you sit back there. You have to answer questions. What is the meaning of this one? Yeah, okay, good. Is that true? That's the meaning, right? That's the meaning of this element. Now I'm asking you, what is the covariance of Z2 with Z3? Where you should look for this number? The second row, third column. This guy, right? That's 1. Covariance of Z1 with Z3 is 0. It's this guy, right? So this is 0. Simple, right? So if I ask you this, it's nothing but you just need to look for the right columns and rows if you know what's the definition. There's nothing harder or difficult or challenging involved, okay? I can also ask you another thing that's just for another practice. So Q with 2P. First of all, what's the dimension of this? 1 by 2, okay? So I will say covariance Q is QP times 2 transpose, right? But 2 with transpose is still 2, right? So I'll just move it forward. That is 2 times covariance of PQ transpose. And I know PQ, so it will be 2, 0, okay? I think once I give you numbers, you somehow all of a sudden find it's much simpler to deal with. Okay, we can also go over the definition to compute them without using the previous result, but for now we can do this. Any questions so far? All right. So what we have learned so far in this lecture is purely probability review. This has nothing to do with Kalman filter. That's our main theme, okay? And the reason we go over this is all about, I'm going to ask you to remember or to have a deeper understanding of conditional density, conditional expectation. And for this, you need to know what is probability, what is expectation. Okay, let's directly move to the second part.